Hi there, welcome to tutorial number 2 on Lightwave Explorer. My name is Nick, and Lightwave Explorer is my nonlinear optics software which I wrote and is available for free on GitHub, both open source and free to download for Linux, Mac, and Windows. And it's a numerical simulation of nonlinear optics. So like many other simulations that we do in physics, we are trying to solve some nonlinear differential equation. When we're numerically solving a partial differential equation, we are by definition doing a approximation if we are doing this on a computer, because we are taking continuous variables like space and time, and we are projecting them onto a grid of discrete points that our computer can deal with. And we are taking this grid of points and putting it into some nonlinear differential equation using finite difference approximations in order to figure out, based on the initial conditions that we put in, how the system that we're looking at ends up. And really what we're trying to do is to get the solution of this equation without coming up with an analytical solution to the equation, because typically we can't if we're bothering to do a numerical simulation. This can be a very powerful thing because, again, we can take some complicated equation that we can't actually solve by hand and actually find out the dynamics and see these taking place and taking them apart and looking inside. But it can also go very wrong because we are making an approximation. If we don't do our approximation correctly and know what this approximation depends on, we can get incorrect results. So if you're going to do it, it's important to know how to figure out which one of these things has happened. The powerful look inside of physics or something very wrong. And they can be sometimes hard to distinguish. Let's look at a simple example. So a nice equation to work with, because it's a nice first order partial differential equation that if you're in physics, you're probably familiar with. That's the time-dependent Schrodinger equation. We know the solution to this already, because we are just looking at, for example, this psi. We're assuming we have a one-level system, basically. So psi is some eigenstate of some Hamiltonian and is just given by this energy epsilon. So what does this wave function do? It just sits in space and spins around in the complex plane, right? So if our psi starts at 1, it's going to rotate around in the complex plane and eventually come back to 1. So it's just sitting there spinning around. We have an analytical solution, which is obviously pointless to solve numerically, but it allows us to look at how numerical solutions actually look in practice. So I wanted to do a quick implementation before we get into the more complicated partial differential equations. I wanted to do a quick implementation of two instructive approaches to solving this kind of thing numerically. So the first thing is something that really you shouldn't do unless you are doing an example of how to badly solve a differential equation, which is Euler's method, which is essentially you say, okay, I have the expression here of the derivative of psi versus time. And if I have my value, I can guess how this is going to go by assuming that the derivative versus time doesn't change. So I just make a linear approximation to move from one point to the next, which for small enough steps is okay, but generally it just doesn't work very well. And something that does work very well is the fourth order Runge-Kutta algorithm, which is slightly more complicated, but also not that complicated. And as you'll see, it is quite powerful. So let's try to do this in Python. So we are going to just make a bunch of functions first, starting with our time derivative, which is going to take sine epsilon. And it's just going to return the time derivative, which is minus 1j times epsilon times psi, and that's it. And we'll make our next function, which is going to give us the next point, starting with the current point. And it's also going to take epsilon, and it needs a time step. And this one is just going to use our Euler approximation and return that, which is you take the current value and you add to it the time step times the time derivative. And that's it. And we need now a function to loop over all the values in the time vector. It's going to start with the initial state, and we just have to give it epsilon in the time vector. So our vector of psi points is just going to start at zeros. same size as t, but t type has to be complex. And we set our time step, just t1 minus t0. And we set the first value of psi to psi 0. And then we're just going to do a loop for I in range. So we start with 1 because we already set 0. And go over the size of t, setting all of the values of psi to our output of our getNextPoint function. And this needs to take the previous value of psi, which is psi I minus 1, epsilon, and dt. And that's it, so I'll just return psi. And that should do it for our function. So let's first plot them, putting them to use. What do we need? Do we need a time vector? Which we set up with linspace, and we're going to go from 0 to 2 pi. Just one cycle of oscillation. Take 20 points. It's one cycle if epsilon is 1. And we have to set our initial value, so that's going to be complex number 1.0. And so first let's calculate our exact solution, which is psi 0 times the exponential of 1 epsilon t. All right, and now our numeric solution we can get from our solve points function. And that should do it. And then we just have to make a plot. So plt plot. We'll take the real part of that. First we'll plot the exact solution. Right, and then we'll plot our numeric solution. And we'll give ourselves a legend. All right, so if we look at this output, well, our function worked, but it's not very accurate, right? So the first thing that we can do in this numeric solution is try to make that assumption that the derivative doesn't change much in the time step better just by making the time step smaller, right? So do 200 steps instead of 20. And it's getting closer, but it's still pretty far off. So what if we do 2000? Now it's getting close, but you can see there's still quite a big difference here. So one more order of magnitude. And now, at least in terms of screen resolution, they overlap pretty well. But you can see we had to do quite a fine step size in order for that to work out. We're just taking one period of oscillation of a cosine. And in order to get that to work out properly, we had to break it down into 20,000 steps, where in a real numerical solution, that's probably not going to be good enough. So let's make a new function that hopefully is going to work a bit better. We can use our same time derivative because that's not going to change. We're still going to be solving the same differential equation, but let's do this with Runge-Kutta instead. So let's do a quick implementation of the RK4 algorithm. So getNextPoint, we'll just make a new version of this called getNextPoint RK4. And this is going to have the same interface. So it's going to take psi current, epsilon, and time step. And now it's going to be a little bit more complicated. So we're going to start by defining a variable k1, which we're going to get from the time derivative function using psi current and epsilon. So just starting off in the same way that our Euler solution did. But now we're going to get another variable, which we'll call k2. This one is also found from the same time derivative. But what we're going to do is we're going to take this psi current and we're going to add to it half of a time step times the time derivative that we took last time. So times k1, and epsilon is still the same. All right, so what we've done is basically we've now taken the solution at the midpoint between where we're starting and where we want to go. And Runge-Kutta has some more steps, so we're going to take another midpoint. Which is going to look pretty similar, except it's going to be based on our K2. And we're going to do one more step. I'll just copy paste here. which is going to be K4, this time making a whole step based on K3. All right, so this is the pattern of our K4. You start by calculating the time derivative where you are, then you do 2 successively more precise estimates at the midpoint, and then you make an estimate at the endpoint. And now we're ready to advance. So the last step of the Runge-Kutta is we return psi current. Now instead of just doing the Euler thing, we do time step over 6. And then we do sort of a weighted sum of these different k's that we've calculated. So k1 plus midpoints gets twice the weight, k2 plus k3 plus k4. And there's our Runge-Kutta algorithm. All right. And we're going to want a new solve points algorithm, which we can just base off of our previous one, except this is going to be solve points RK4, and it's going to just use this function instead. So now we have our functions. So let's go back to this case of 20 where like this guy was pretty inaccurate. And now we can just plug in our new RK4 based propagator and try that out. And now you see with 20 points, it's a lot better, right? So even with 20 points, these lines are just on top of each other. So when things are this close, you can't really tell by eye how well things have converged. So let's try to look at this convergence numerically. And we can do that just by looking at the error, which is going to be the difference between these two curves, the exact and the numeric solution, and how that varies with however many points we use in our calculation. So let's just do a loop over point numbers. And we'll just make an array. And we'll just try a bunch of points. And I'll do sort of a logarithmic-ish scaling here just to make it easier to plot on a log scale. 5,000, 10,000. That's enough for now. Okay, so we'll do 3 orders of magnitude. I'll put my line breaks in the right space. And we will keep track of our errors because that's what we're going to want to plot. We'll just zero this out. This will be the same size as point numbers, but it's going to be complex. And we'll do similar vector for RK. And now we'll just loop over again all these values. So for I in range 0, point number size. We're going to need a new time vector t at each point. So p.linspace, again, 0 to 2 pi, number, and then, yeah, so we'll just call that numeric, and that'll be solve points. So this is our Euler function from before. And this is always going to be using that t, and then we will have our RK version, and that will use the RK4. And now we just keep track of the errors, and because we are solving this thing over one period of oscillation, we know what the solution is at the end here. It's just 1 again. So we can just subtract 1 from this in order to get the error. I'll just look at the endpoint, minus 1. Then we'll look at our errors, our Runge-Kutta. There we go. And that's our loop. And we'll just plot these log scale. Absolute value of error. And we'll call this one Euler. Now we'll plot our RK. And that should do it. Draw a legend. And how does that look? Okay, so now you can see what's going on here. The RK4 solution has significantly less error at low values, and you can see on the log-log scale these things have different slopes. You change the number of points over which you're solving, or you're decreasing the size of each step by 3 orders of magnitude, and the Euler solution gets more accurate by 3 orders of magnitude. Whereas RK4 here, it starts more accurate because it's derived by canceling some of the leading error terms, and it only gets more accurate from there. You can see the gap between these, and this is a log scale. The gap between these is growing by quite a lot. So you make the step size smaller by 3 orders of magnitude, and the accuracy gets better by 12 orders of magnitude here. And that's because RK4 is called RK4 because it has fourth order convergence. So as you make your step size smaller, your accuracy gets better to the fourth order of that change, which is pretty powerful. So once you converge an RK4 solution, you can be pretty sure that it's converged, whereas Euler, you always have a ton of error sort of creeping around, and you're never really sure what's converged and what's not. Now, if we keep going with this, in the end, what did we just learn? We saw that both of these algorithms can give you something that looks right. And by look right, I mean on the monitor, you don't really see a difference between the two curves, the one showing the exact result and the one showing the numerically computed result. However, you need a lot more points to do this with Euler. So we needed about 20,000 to get something that looks visually good, and we could see numerically that the Euler solution was always inferior, and as you made the step size smaller, the RK4 solution didn't really need it, but it actually got better faster than the Euler did. So this raises the question, in practical terms, how do you know when you're in the good enough range? And to do that, I think it makes sense to look at a physical example inside of Lightwave Explorer, which we'll do right now. All right, so let's have a look at convergence in situ in Lightwave Explorer. So I've set up a simple simulation here where I'm just solving for second harmonic generation in BBO. So what I've done is we're putting in a pulse of light at 1 micron, kind of a short pulse, like a 20 femtosecond pulse, and sending it through a 300 micron thick BBO crystal and making some second harmonic of it. And we're doing it at a fairly high intensity in order to get a high conversion efficiency of the second harmonic. So if you look at the bottom panel here, this is what remains of our input pulse, which is on the slow axis of the crystal, and on the fast axis of the crystal, we've made our second harmonic. You can see that sort of reflected in the spectrum here. Let me put in a spectral range, which makes sense for looking at BBO, at least to the level of detail that we're interested in at the moment. So 0 to 1400 terahertz just sort of puts us in the range of frequencies where the Sellmeier equations that I'm using for BBO are actually valid, right? And we'll look at this on a log scale, maybe from 10 to the minus 20 to, let's see, our top is maybe 3 times 10 to the minus 8. And we'll put it on a log scale just so we can see all of the spectral details of our higher order mixing processes. So what's going on inside of the crystal is we're not just making the second harmonic that we're interested in. Because the second harmonic gets so intense, we, for example, have a cascaded third harmonic, which isn't phase matched, and also a cascaded fourth harmonic, which also isn't phase matched. You can see they're getting progressively weaker as they go along, and at even higher frequencies, you do even have some of these higher order mixing processes just on the edge of reproducibility. So again, I have more than 12 orders of magnitude in intensity here. So in reality, there would just be a few photons at these frequencies, but because it's fully resolved, we can see these lines. And when we checked for convergence, actually, this is where all of the trouble is going to be at the highest frequencies if we want to actually have the results be valid there. So one thing that we can do to look at convergence is first, let's check how it behaves against our actual step size. So this is equivalent to what we were looking at before in terms of the number of steps in the Runge-Kutta algorithm, because right now we are looking at a result which is done with the unidirectional pulse propagation equation. So this dz tells us the step size, and we can, for example, scan this step size. This is the easiest way to look for convergence. So we can just set our batch mode to give us a scan of DZ. And we can say scan from 100 to 500, and we'll do 5 of those steps. So we just see each one of these come about. And you can see something flashed up, right? So just along the edge at the very bottom of our scale, there's a little bit of noise which is happening. And this higher frequency, something funny happens there, right? Because this is really just at the edge of where things are working. If we make our step size a little bit longer, you can see that that guy is actually changing quite a lot. If we were to go even smaller, for example, if you were going to go to, say, a 50 nanometer step size, now that and 100 are really quite identical in terms of the output that we get. But if we make this a little bit longer, like 200, well, it didn't change much noticeably. But if we go up to 300, that's when you could see that one started to change, right? So if I was going to publish something based on this, I would really take this number down until the point where really nothing is changing. Now, if you're just doing a study on your own, one thing that you could notice is, like, even though this value up here, the high frequencies, that was changing, but actually those frequencies aren't too relevant for what else is happening in our region of interest. Because like I said, this thing, this blob that shows up at high frequencies, it's kind of an artifact in itself because it is light which is showing up at a frequency where the Sellmeier equation that we're using to describe the refractive index of the crystal is just not valid anyway. So this result in any case, I wouldn't make any conclusions on the behavior of this high frequency because the Sellmeier coefficients that I'm looking at just aren't valid there. So I don't phase match this properly. But what I do want to make sure is that there isn't any cascading of generating light at the spurious frequency and then having it affect the rest of my simulation, because that's when things can start to go wrong. And that's when, for example, if I have a larger step size, like 500 here, trying to find one of the ones where it gets really dramatically wrong. Yeah, so at this particular step size, there is a good amount of noise which just accumulates here. So something at this frequency actually diverges because its parameters are so out of spec. And what could happen here is if this simulation were to, say, go on longer, like say we did a 500 micron or 400, 500 micron crystal, let's do 500. Well, it's actually not doing much. So the result still seems actually fine. But let's go back to 300 because we're actually not gaining efficiency with a thicker crystal at this point. It's depleted. What we don't want is that this spike outside of our region of interest affects the light inside of our region of interest. And you can see, like, it actually still doesn't matter. If I go back to 200 here, all it did is change a little bit down here at the level of single photons on the log scale. So it's basically just changing the noise. So it's still fine, but you can see it. So it's better to really eliminate it if it's a result that you're going to be basing conclusions on. So let's say with 200, that's converged. But now you can see, okay, this frequency is pretty high compared to the grid. So just looking at this plot, which maybe I can explain a little bit more. This plot, if you hover over it, it will tell you. This is the Fourier transform, like the two-dimensional Fourier transform of the electric field. So it's versus frequency still, like this x-axis is frequency, and the y-axis here is the transverse angular momentum. This is a map of our k space. Up to down is k, and across is frequency. So this is our dispersion, you can put it that way. And this frequency here is quite close to the Nyquist frequency. Nyquist frequency is the highest frequency that can be represented on this grid. And this is by purpose because this is the highest sort of strong peak that would show up in our simulation. So what's going to happen if I start making the time step a little bit larger? Now, the time step in the case of the unidirectional pulse propagation equation isn't something that we are propagating over. It is just a parameter of the grid which we propagate. But that doesn't mean that we can't get this wrong. So let's make this a little bit larger. So add a 5 there. And what should happen is this spot should get a little bit closer to the edge of the grid because the Nyquist frequency is coming down a bit. So we run that, and that's what happens. So nothing unexpected happens yet. But let's go to, say, 2.8 now, or 0.28. Now it's right on the Nyquist frequency, right? And now if we keep going a little bit more, so making our step size even larger, now you can see it's actually moving the other way, right? If I now go to 9, right, you can see what's happening. So this little blob is moving closer to this frequency, but that is not what should be happening. Like they should maintain their spacing independent of the step size. So what's happened now, this is what is actually called aliased. That means its frequency is too high to be represented on the grid, so it ended up at a different frequency of the grid. So it's actually propagating at the wrong frequency now. And if I keep going, say we put in 0.3 as our step size, it'll get closer and closer. Right now it still doesn't matter because it's not mixing with anything. You can see that all of our frequencies in our band of interest are still fine. But if I keep going with this, now I put it on top of one of our other frequencies, right? And now our spectrum changed because it's interfering, right? So if I go back to 0.3, you can look, it's actually changing the stuff around it. 3.5 is a little bit too much. Let's try to get it right on top of that other one. Yeah. Now it's changing the shape of this spectrum. Let's try 3.3. Right? It's interfering with this spectrum. So now this thing, which is in our region of interest, is now wrong because this higher frequency has aliased on top. So let's put this back to 2.7 so that it's back where it belongs. So this is another thing that you have to look out for, is if you have any aliased frequencies. And really the easiest way to look for this is if you change your step size, your time step size, you should keep the same spectrum. And if your alias stuff is moving around, you will typically be able to see it just because the shape of your spectrum is changing. Just because of the nature of Fourier transforms, the shape of your spectrum should be independent of the step size you're using. The step size should only determine where is the Nyquist frequency of this simulation. So you should be able to freely change this parameter and end up with the same spectrum. I mean, maybe some of the discretization parameters will change and whatnot, but otherwise this spectrum is going to be the same spectrum, right? So watch out for that. Watch out for these high frequency things that might get aliased onto low frequencies in your region of interest. All right, and for other aspects of our grid, let's look at the time dimension. So you can see that these two pulses are sort of nicely resolved here on this grid. Like they both go to 0. They're not leaking out of the time grid. I mean, what can happen if you, say, do a very long propagation? The time window is going to be locked to the carrier frequency of the pump pulse. So these are going to drift back a bit with a longer propagation through the crystal. And what's going to happen is this blue pulse, this second harmonic, which is on the fast axis, it experiences more dispersion. It has a slower group velocity. It eventually is going to fall out of the time window. And because this is on a Fourier basis, you don't have to worry about this if you're using the FTTD modes, but unidirectional pulse propagation uses Fourier transforms. And it's on a periodic boundary condition here. So if it falls out the back, it just comes back the other side, which is usually fine unless you get really crazy with it and it goes all the way back around, and now it's overlapping with the original pulse again because it's gotten so dispersed and so delayed by the group velocity. And now something unphysical is happening. The pulse has wrapped around in time and it's overlapping with the original pulse again, and this can affect the phase matching. So you want to make sure that your time window is long enough that doesn't happen, that you don't wrap around in time and find a pulse that you shouldn't be able to find just by adding delay. And you fix that just by making this longer. So if we go back to 500 here so that it's starting to come back around, of course, if this was a bit longer time window, then it has no chance to leak around and do that. So that's the size of our time window. So really it's just the time window has to be long enough that your pulse isn't sort of wrapping back around and doing some weird interference where it shouldn't. So that's our time grid. Now let's look at our spatial grid, which is actually a little bit simpler to look at. So let's just do our base calculation first. go back to 300 here. All right, so here's our nicely converged, nicely efficient second harmonic generation. What happens if we change the parameters of our space grid? Well, one thing that we can do, this max x just says how big the grid is in space, and we just don't want it to cut the edges of the beam. If we make it too small, say 512, it's going to start to cut the edges of the electric field. So let's do that. You can see by eye here, it still looks okay, but this K versus frequency plot, this is on a log scale. And on a log scale, you see this line that shows up here. If I go back, the line will disappear, right? There's that line there. That line is what shows up when you cut the edges of your spectrum. It's essentially you've imposed a hard edge on your beam in space, and a hard edge in space is basically spectrally flat versus angular momentum, so it will bleed out unnaturally and give you this trail heading out to infinite K, which is just a very clear warning sign that you've cut your beam. But that one's super easy to fix. You just have to make your beam size big enough that it fits, and that just immediately goes away. It converges very fast. And a similar phenomenon will happen if your step size is too big. You can see that in K space, this sort of nicely fits within the grid. If we make our step size twice as big, it won't fit inside the grid anymore, and we'll see, well, there's stuff at the edge of the grid. And again, this is an easy one to fix. If there's stuff at the edge of the grid, then your step size is too big. And you can sort of see that in space, that this beam is just way too chunky for what's going on. So you just have to make your step size a bit finer, make sure everything within K. And now we have a nicely converged simulation, right? And we can make our step size, say, twice smaller, and we get exactly the same result. So this is kind of where I would work if I was being serious about this result. So at this point where I know that I can make my step size twice as big and my result is still the same. And if you're scanning some parameters, say if some of them are getting more extreme, always check this at multiple points along your spectrum, just to make sure that you're actually converged. Because this is important. It's a numerical approximation at the end, and you want to make sure that the parameters that you're putting into this approximation are somehow adequate to describe what you want to look at. Let's wrap things up with a checklist of things that you should go over to make sure that you're doing your numerical simulation properly before you publish or even believe the results. So first, is the grid good? Does it contain the full beam without clipping? Does it have a small enough transverse step that you sample the full K space of the beam? Is your time range long enough that the pulse doesn't wrap around on itself? And is your step size in time small enough to avoid aliasing? Then you should look at what are the observables that matter and identify how they change with step size, and preferably that they don't change with step size. And this step size that's relevant in the unidirectional pulse propagation mode is dz, space in the propagation direction, and in FDTD mode, it will be dt, the time step. And are they the same if you double the step, so you know that you're solidly in the converged range? And so if you follow these steps, you should be able to come up with simulations that are actually teaching you something about the inner life of the system that you're looking at, and not some nonsense from bad numerics. All right, so that's it for today. Take care.